comes from Miles O'Brien here on Twitter, who asks, what sort of instrument could be used to answer the question of whether these planets harbor life? Could Webb do it?
Sure. So Webb has a suite of instruments that cover, wavelengths from sort of the near infrared all the way through farther into the infrared spectrum. But in particular, it has a lot of very powerful spectrographs aboard. So this is going to allow us to do this transmission spectroscopy technique that I talked about earlier. And it covers the right wavelength range where we can start to detect molecules like water, methane, ozone, and oxygen. So we can start to do a lot of what Sarah had suggested in trying to determine habitability and also the potential of it harboring life.
And I just want to add one thing, and to Miles and everyone out there, is we really try to emphasize we have the capability to find signs of life elsewhere, but nature has to deliver. And because it's also new to us, these red dwarf stars, we don't totally know what's out there. So if nature has made life ubiquitous, and there are lots of atmospheres without clouds, substantial enough accumulation of gases, we'll have no trouble finding it at all. But if it's the opposite, then it may be a while. But I did want to add one more point that we hadn't covered yet, that we have the TESS mission upcoming. We have other ground-based searches. So TRAPPIST-1, we're just here as the first. It's the most exciting one so far, but we hope to have many more of these and lots of chances to find signs of life in the future.
Wonderful. Next question here comes from Twitter user Chris Sims, who asks, is it possible to listen to this planet system using our SETI-style telescopes? How do we learn as much as possible?
Okay,
to my knowledge, it was already listened to by SETI, and they had no signal from artificial signal detected. So it's doable, but there's no signal detected.
Great. Next question comes from Twitter user Sawyer, who asks, how far into the foreseeable future until we might be able to see a craft that can actually make the journey to TRAPPIST-1?
This is a really hard question, just because it requires so many miracles on the way. See, when James Webb was developed, the way I think about James Webb, it required something like 10 miracles, kind of things we had never done, and kind of put it together into a telescope, with a 6.5 meter kind of foldable mirror and a thermal system that's a tennis court in size. Kind of how do you do that? The answer is you start inventing your way forward. This a question that's being asked may be a 100 miracle type of question, and some of them probably relate to nuclear propulsion. Some of these miracles relate to radiation protection. They relate to things that we're just starting to push at. Now, the good news is there's a lot of work that's being done on kind of the first 5 to 10 of those miracles that are being looked at, not necessarily because we have our eyes set right now on going to a star. It's a big leap, but because we're looking, for example, at the outer solar system. We want to get there a lot faster. We want to get there with more payload. We want to get there with more energy. And so the way this game works, it's really, it's leaning forward. It's really, just because it takes 100 miracles, not backing up. That's really what I would believe is what NASA is all about. And that's also what led to this kind of discovery in many ways. Spitzer itself had a whole bunch of miracles on detectors and systems, and the same is true for the other question.
I'd like to just very briefly mention our colleagues at the Breakthrough Foundation and the project called Starshot. And you can go look that up and see that they're planning 19 miracles to figure out a way to send very tiny and thousands of little tiny spacecraft flying by the very nearest stars. That would be Proxima Centauri, not quite like TRAPPIST. But I just want to remind all of you, although it may sound discouraging, perhaps that in our lifetime we won't have a way to see how to get to TRAPPIST-1, that we're here because we have these big sophisticated space telescopes, Hubble, Spitzer, James Webb, and future ones, and we're big on remote sensing. So even though that's what we have to live for, we are still very excited about the possibility of using our telescopes to see what's there, rather than we have to leave the trip there to future generations.
We've got a lot of questions on social media, so we're just going to keep them coming. Jason, what other questions are we getting?
Sure. This next question comes from Twitter user Aku, who asks, any estimations on how old these discovered exoplanets are?
Yeah, the age of the star and the system itself is poorly constrained. We know it's not very young. It doesn't show signs of youngness, so it's at least 500 million years old. But we can't say more because these ultra-cool dwarf stars, they evolve super slowly. Their lifetime is 1,000 times larger than for a sun-like stars. So we don't see them evolving, so we can't constrain their ages.
All right, this next question comes from Facebook Live here. What is the distance between these 3 planets? Is it something like 500,000 kilometers? And what is the distance between E and the star?
Oh, the distance between the planets are a few times the distance between the Earth and the Moon. So we're talking about something like millions of kilometers and not hundreds of millions of kilometers for an Earth around a sun-like star. And for the planet F, or E, the distance is something like 5% the distance between the Earth and the Sun. So it's much, much closer to its star.